Hello, I'm Joe Hamaker, and in this presentation, I'll be discussing the cost of human rating space projects. First, a little bit about me. I'm the director of DoD and NASA programs at Gallerath Federal. Formerly, I directed costs for NASA, and I have over 40 years of experience with cost estimating and analysis. My email address is at the bottom of the chart, jhamaker@gallerath.com. First, let's discuss some engineering aspects of human rating. The structural factor of safety for human rated systems is generally higher than for non-human rated systems, typically 1.4 and 1.25 respectively. Now, this is going to be partially accounted for in your cost analysis by higher structural mass that you're going to be given. But assuming you're using a parametric cost model, you might also need to set some of the complexity settings in the model to reflect the more stringent structural analysis that's generally associated with human rated systems. Higher level redundancy is going to be required by human rated systems. Once again, this is going to be partially accounted for by the mass that you're going to be given, but you may also need to consider a complexity rating here due to the cross-strapping that's going to come along with the additional redundancy. There's going to be a higher parts quality associated with human rated systems, which your cost model may need to take into account, your cost estimate may need to take into account. There are going to be more formal and prescribed design and construction standards. There are going to be more stringent safety and reliability analysis. The software is going to be held to a higher standard. Now, to some extent, this is going to be partially accounted for by higher software lines of code count. But once again, you may need to consider the complexity of the software. The software complexity is going to be higher because it's going to have fault detection and notification, software independent verification and validation, abort triggers, and so forth. Human rated systems have a lower G-load tolerance than non-human rated systems. This is not anything you'll really need to account for in your cost estimate. Presumably the design that you're going to be given will automatically reflect that. Human rated systems have higher biological and toxicity requirements. They have more documentation, more reviews, formal certifications, more configuration control, traceability, and just in general, more systems engineering than non-human rated systems. So you need to make sure you take that into account in your cost estimate. Now, there may be many more things different between human rated and non-human rated systems than I've listed here, but we don't really need to completely enumerate the differences because, as you'll see, we're going to derive a factor that's going to include them, whatever they are. Now, let's take a look at that red font in the oval on the chart. The differences that I'm talking about here are over and above the physical differences, such as probably the requirements for an escape system for a human rated system, maybe the requirement for some early on uncrewed demonstration flights, and certainly the additional systems required for humans, pressurized structures, environmental control and life support, crew systems, and so forth. All those are going to be required, and they will have to be in the design that you're estimating. The factor that we're deriving here is not going to take into account those factors. It's taking into account the factors that are on the black font part of this chart. I'll mention that point again a couple of times. So our objective and purpose here is to derive a factor from historical space missions that represent the cost of human rating, kind of a magic wand factor. Now, why would we be interested in such a factor? Well, for one thing, to be able to use automated spacecraft cost models that are not based on human rated systems. If we could use those costs to estimate human rated systems and then use our magic wand factor here to make an adjustment, that would be a good thing. Well, why is that a good thing? Well, because there are a lot more automated spacecraft models with more data and more features than there are human rated systems cost models. And this is all made worse by the lack of International Space Station and Artemis cost data. So having such factors would give us more comprehensive ability to do cost estimates, trade studies, and sensitivity analysis using automated spacecraft models, and then adjust the cost at the last step to account for human rating. Now, once again, I'm mentioning the same point I made before on the previous chart in red font, that the factors I'm talking about here only account for human rating, with emphasis on the word rating there, and not the extra subsystems and so forth that would have to be part of a human mission, which are going to be part of the design that you'll be costing. All right, I use a database here called the NAVCOM Cost Model Database. NAVCOM is an older NASA cost model. It stands for NASA Air Force Cost Model. It had the version I used had 113 total historical data points, 93 of which were automated spacecraft. And of those 93, 71 were Earth orbital spacecraft, 22 were planetary spacecraft. It also had 11 launch vehicle or upper stages or engines in the database. And in this study, I characterized any of those as launch vehicle related. It had 14 human rated data points, which is what we're really after here. Now, those numbers don't add up to 113 because 5 of the launch vehicle related data points were also human rated. Okay, so why am I using this older database? Well, because that's where the human rated missions are. As I mentioned, regrettably, NASA has not collected ISS or Artemis cost data. What NASA has collected, though, is a lot of modern post-NAVCOM automated spacecraft data points with the CADRE, the Cost Analysis Data Requirement Database. So why don't put those in this analysis? Well, because of incompatible ground rules between the old NAVCOM data, where the human-rated spacecraft are, human-rated missions, and the new, more modern CADRE missions. For example, full cost accounting. NASA went to full cost accounting back in fiscal year 2004. So the NAVCOM database does not reflect full cost accounting, whereas the CADRE database does. And so to use the NAVCOM and blend it in with the CADRE data points would require adjusting the old NAVCOM database to full cost accounting, which could be done, but it was more trouble than I wanted to take for this exploratory, more or less example analysis and study here. Okay, so the analytical approach that I used is regression analysis. I introduced indicator variables for 3 categories. The first category is human rated, and introduced that because that's what we're interested in this study, is human rating. I introduced another indicator variable for planetary, yes or no, for 0 or 1 for planetary, because we know from experience that planetary missions are from a different family than Earth orbital data points. They have higher cost. So we need to statistically control for that phenomenon. And I've mentioned launch vehicle related. That also needs a control variable. In this case, launch vehicle related, the NAVCOM database means the launch vehicle stages, upper stages, rocket engines, solid rocket boosters, the shuttle orbiter, the shuttle external tank, and the shuttle solid rocket booster. Now, right now, you're probably thinking, well, why do we even have those data points in there? Maybe a better approach would be to omit some of these launch vehicle data points out of this analysis, arguing that they're too unique from their siblings. And that's certainly true. But I left them in this analysis because it gives us 5 additional human-rated data points. It's increasing our 14 human-rated data points from 14 to 19 if we leave those other items, launch vehicle-related items in. So these 5 data points were too precious to lose since we do not have ISS and Artemis cost data. So the regression analysis is shown here. This is for DDT&E, which stands for Design, Development, Test, and Evaluation Cost, aka development cost. You see the regression is logarithm of DDT&E equals a constant term, 0.315, with logarithm of mass having a coefficient of 0.672. And then you see our 3 indicator variables, human rated or not, with a coefficient of 1.22, planetary or not, with a coefficient of 1.55, and launch vehicle related with a coefficient of 0.947. Now, the reason for the logarithms here is we know from experience that mass follows a power equation in space cost analysis. So it's y equals ax to the b equation form. Thus, we need to do these logarithmic transformations. Now, when we did the regression here, all our independent variables passed the t-test, and that's shown in that oval there. The p-values are the t-test, and for t-test, you want generally you want something like a 0.05 or less. The lower the better. Mass is 0.00, which is great. Human rated is 0.007, which is also very good. Planetary is all zeros, that's good. And launch vehicle related is 0.022. So all those pass the t-test, and we get an overall R-squared adjusted 66%, roughly 66% here. So this gives us a workable CER to predict the effects of not only human rating, but we get planetary and launch vehicle related kind of thrown in for free, as we'll see in a few minutes, and we can develop some factors there. Here's the same analysis for the regression of the theoretical first unit, TFU, sometimes called T1 or just first unit cost. Now, First thing we want to look at here is those p-values again. We notice right away that human rated has a p-value of 0.737. So that's much higher than our cutoff of 0.05. And so that's an unacceptable p-value. But if we look at it a little bit more, we see that not only that, human rating has a negative algebraic sign. So it's an illogical algebraic sign. It's saying that human rating a system makes it cost less money than non-human rating. And also, if we keep on looking at that equation, those terms, we'll see that launch vehicle related also has an unexpected negative algebraic sign. So this is telling us we need to do something with this CER. And what we need to do is omit human rating from the TFU CER. So if we do that, leaving out human rating, we now get an acceptable CER. The launch vehicle related sign flipped to positive. All our p-values are good. And our R-squared adjusted is acceptable at 69%. Now, while leaving out human rated is going to give us a tool on the production side that does not allow us to predict the effects on production cost of human rating, we can still exercise the CER for its predicted effects of planetary and launch vehicle related. And if you think about it a while, maybe it's not unreasonable that human rating does not drive recurring cost all that much. We have already said that the structural factor of safety may be being explained by mass, and the same point for redundancy. All right, so we can exercise those two CERs from the two previous charts to give us a table of factors, as shown in the table below. Now, for every one of these factors, I had to use a mass, right? That's one of the principal inputs, independent variables of the two CERs. So I just chose to use the mean of the NAVCOM database. It's arbitrary. It doesn't affect the derivation of the numerical value of the factors. So that mean mass happens to be 3873 kilograms. So let's look at the first row of the table down there. And we see we have our categorical variables mentioned first there. I'm saying the first row is human rated, no. Is it a planetary mission? Let's set that to no. And is it a launch vehicle? Let's set that to no. So I'm really following the enumeration of factors that you see in the second bullet on this chart, 0, 0, 0, comma, 0, 0, 1, 0, 1, 0, and so on. Those are the 8 sets of possible switch combinations that you can get if you have 3 binary factors. So row 1 is our home base. It's a regular Earth orbital satellite. We exercise at 3873 kilograms with the 3 switch settings to no. We get a development cost there in millions of dollars that you can see. We define that to be a factor of 1. We get a TFU cost, as you can see in the table. We define that to be a factor of 1. So once again, this is a non-human, non-planetary, non-launch vehicle setting, and so therefore it corresponds to an Earth orbital automated spacecraft. Row 2, we use the same mass. This time we're going to set that third switch setting to for launch vehicle to yes. That's the 001 enumeration in our list there. We get a new development cost, a higher development cost, and we get a lower TFU cost. The reason we get a lower TFU cost there, my hypothesis is that in general, on the launch vehicle production side, the production of launch vehicles, they're optimized for production costs because we know we're going to build dozens or scores or hundreds of launch vehicles. And so they're more optimized for the production costs. And so therefore their cost is less than a Earth orbital automated spacecraft on the production cost side. So we're getting a factor there of 0.2. The factors come from taking the $910 million of development and dividing it by $353 million of development from our home base row. So it gives you the 2.6, and the 0.2 is 249 divided by 1173. So row 2 then corresponds to a crew Earth launch vehicle, a human rated Earth launch vehicle. Row 3, let's set the factors to our third enumeration, 010, which says it's not human rated, it is planetary, and it's not a launch vehicle. We see our development cost result there and our factor of 4.7 compared back to our home-based row. We see a new TFU cost and a factor of 1.9 compared back to our home-based row. So this is a non-human, planetary, non-launch vehicle, AKA a planetary automated spacecraft. Now, I'm not going to walk you through the rest of the table there. I think you can follow that logic. I will point out in row 5, our switch settings are yes for human rating, no for planetary, and no for launch vehicle. So this is a human non-planetary non-launch vehicle, or AKA a human-rated Earth orbital spacecraft, which was the original question that this study sought to answer. So if you do those switch settings, you get a development cost of $11.96, which is a factor of 3.4 compared back to row one, and a production cost of $11.73 compared back to row one. Now notice we've seen that $11.73 before. Well, the reason for that is the human rating independent variable, recall, it was not in the TFU-CER. We could not get that in with a statistically significant acceptable t-test. And so human rating is not in the TFU-CER. So when you flip the switch back and forth on human rating, you see no difference in the TFU cost because our TFU-CER is blind to that. Okay, so I want to make the same point I've made before in red font at the bottom of the chart. Remember that adjusting an Earth orbital automated spacecraft to a human-rated spacecraft with that 3.4 factor, and this is true for any of the other factors in the table, we're only accounting, the magic wand factor is only accounting for the rating that we discussed back on slide 3, and not any extra subsystems and so forth that would have to be part of such a mission. So your cost estimate will presumably be presented with a design that includes those extra subsystems. Okay, conclusions and observations. The original intent of this analysis was satisfied by deriving that 3.4x factor on the previous slide, and that got us from Earth orbital automated to Earth orbital human rated. But the regression analysis allowed us to develop a total of 8 factors for 8 categories, 7 additional categories. Now, the 3.4 factor, by the way, is higher than what's reported in the literature. There's an August 1991 study cited there by Holly and Pine, which gave a range of 1.77 to 1.86 for our human rated cost factors, which is a bit lower than our 3.4x here. There's an associated 1991 NASA Johnson Space Center memorandum by John Young, and yes, that's the famous astronaut, NASA astronaut John Young. In his memo, he mentions a range of factors, 1.56, 1.67, and 1.77. I think the root data there may be the same as the Holly Pine study. There's another NASA study out there, I believe about 2010, called Cost Impact of Crew Rating Heavy Lift Launch Vehicles by Andy Prince and others, which suggests a factor in the 1.3 range. But that study also mentions an average factor of 2.5 from going from unmanned, what they call at that time, unmanned spacecraft to human-rated spacecraft, 2.5 from one model that was cited there. I couldn't find any other studies examining the other 7 categories of this analysis. For example, one factor we saw on the table a moment ago, if you happen to see it, was a factor of 41 from going from an automated Earth orbital spacecraft to a human-rated planetary launch vehicle. Now, I'm not saying that factor is accurate. It is what comes out of the NAVCOM database. And we do know that going to a human-rated planetary spacecraft would be presumably expensive. So maybe the factor is certainly in the right direction. I have a number of thoughts how this analysis could be improved in the future. One, if we could get International Space Station and Artemis cost data, we could blend that into the study, especially that would all be human-rated data, and that would be a lot more human-rated data. If we did that, we might want to go to the trouble of adjusting the NAVCOM data to full cost accounting, which would allow us to continue to use that. It would also allow us to include those more modern automated spacecraft from the Cadre database and from other models such as the Galileo-SEER space models. And if we did all that, we could probably leave out those pesky launch vehicle related NAVCOM data points, such things as rocket engines, shuttle SRB, and other points. We could throw out those quote unquote precious human rated data points if we had the ISS and Artemis data to substitute in. Okay, there's my email address again. Feel free to contact me if you have any questions. Also, Galer's website there, and some of the other types of cost analysis that we, Galerith, a 75-person company devoted to doing various kinds of cost analysis for our customers. Those cost analysis our capabilities are listed on this chart. So thank you very much.